Hello, welcome to Math 251, Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will take an overview of section 2.5. This is the formal definition of a limit. Formal means a mathematically structured definition, and that does not really rely on graphs or numerical values. We're looking at the idea behind limits requires a mathematical sense of thinking. Now, if you're not a math major, this section will probably not be so important because it dives deep into the mathematics behind calculus. So a lot of times when people go through calculus, they just do the computations for finding, manipulating your functions, finding derivatives and integrals and things like that. But deeper in mathematics is the idea of limits, and people usually call it the epsilon delta definition of a limit. And so we will try to describe the epsilon delta definition for a limit and apply the epsilon delta definition. And then we'll also dive a little bit into the one-sided limits and infinite limits using epsilons and deltas. And then when you dive deeper into mathematics, you'll actually have to prove some of those limit laws that we were looking at. Those limit laws weren't really proven, and the way to prove that limits do exist is to use epsilons and deltas. So epsilons and deltas, what are epsilons and deltas? The definition of a limit is given by this, and we can read the top part. F of x is defined for all x, maybe everything except maybe possibly at x is equal to a, and some open interval containing a. And then the limit as x approaches a of f of x is equal to L means, and this is the epsilon delta limit now, this is where it becomes really mathematical. It says for every epsilon bigger than 0, there exists a delta also bigger than 0, such that if 0 less than absolute value of x minus a is less than delta. So that's saying, this statement here is saying that if we pick an x value that is reasonably close to a, and by reasonably close we can say that's within delta apart, then the difference between the function evaluated at that x value and the limit that we're saying, the difference there is going to be less than epsilon. The idea here is that if you let epsilon be small and get smaller and smaller and smaller, if you can continue to find a delta so that this is going to be true, then your limit will exist. And so there's some graphs here that try to describe that idea, where you have some epsilon, you're guessing what your limit is equal to, and then you choose a delta. Delta could be as big or as small as it needs to be. But as epsilon gets smaller, you can still be able to capture it using delta. All right, so there are some apps that allow you to view this. That's given in the textbook, so I encourage you to take a look at those things. Now, fortunately, they give us a kind of like an algorithm of sorts. Here's our strategy for proving that a limit does exist. First of all, you have to have that limit L as your best guess for a limit. And then you begin the proof by saying, let epsilon be bigger than 0. And then once you do that, you have to find a relationship between delta and epsilon. So delta has to be some value that you're going to find, and then you're going to begin the restriction on delta by saying the absolute value of x minus a is less than delta. Now the 0, saying that this value x minus a is bigger than 0, or 0 is less than the value, absolute value of x minus a, all that means is that we're not going to be focused on when a does equal to x. We're not looking at the exact point. We're looking at the points around it. And so that's why there's a 0 less than included in your inequalities here. And what we want to do is go back to this expression f of x minus L. Now again, L is some limit that you would have already found, and then you're just actually proving this using epsilons and deltas. And so given this expression f of x minus L, you kind of algebraically manipulate this so that you get the expression x minus a coming out of there, and then you're going to relate that to delta. Okay? I think it's best if you take a look at some examples in the textbook. They have good examples. The problems that you might see in the homework give you a step-by-step process, so you don't have to do everything from scratch, at least not in the beginning. And then once you do a few of these, you kind of get the flow of what you're looking for and how you'll eventually have to find it. Now this also would apply for one-sided limits as well as infinite limits. So the one-sided limits just say that you're going to be going from one side, and then you're going to keep your delta, not delta being within the interval, but delta just being on one side of the interval. As for infinite limits, that's handled a little bit differently, in a sense that you can say that the limit as x approaches a of f of x is equal to positive infinity if, and here's a statement now, for every m bigger than 0 there exists a delta bigger than 0, so that if 0 is less than x minus a in absolute value less than delta, then your function is going to be bigger than this m. And likewise, if it's going to negative infinity, it's going to be less than negative of that m. So again, these ideas are based on epsilons and deltas. Now I know this doesn't have an epsilon because you're not getting close to it. You want to go above it. You want to go to positive infinity, or in the case of the second statement here, you want to go to the negative infinity. Okay? All right. So this overview of section 2.5 is really kind of a little bit more advanced than we would like to go over. So I would probably want to look at this as an optional section. If you're going to be a math major, or if you want to challenge yourself with some mathematical thinking, you'll dive deeper into this formal definition of a limit. If not, I think this is something that will not be covered in any of our exams, and so we will kind of keep this kind of optional for us. Okay, so that is your overview of section 2.5. Good luck with this chapter.